So we invite Manuel Perez-Mato, and he has been famous in the developer of the Bilbao Crystallographic server, and also he has been working on the superspace formalism of the modulative structure analysis. And now he is the chairperson. Now he's the chairperson of the Commission of the Magnetic Structure Analysis by IUCr. Okay, so let's welcome him. Thank you very much.
Thank you. First of all, I must say it's a pleasure and an honor to be here and to have the opportunity to talk a little bit about magnetic structure symmetry and the developments that in the last years I think have improved quite a lot the methods on this matter. And first, I would like to know more or less what is your background, because this depends also how fast I could speak or how much. And may I ask you, for instance, how, if you can raise your hand, if you have already determined or work in the determination of an ordinary structure, not magnetic one. Could you raise your hand if you have worked on that? Okay. And can you raise your hand also if you have worked in magnetic structures already? I mean, the analysis of magnetic structures. Okay. So not many. And raise your hand, please, if you have done some course on basic crystallography. Okay. Higher, higher, please. Put your hands higher. Okay. Thank you. Thank you. So I think, as we have feared, there are many different levels of background that you have. So I must excuse myself for those that you may find what I'm going to talk maybe too basic, that you know already about. But in order that everybody can follow, I think we should start for some very simple things. And the first thing is that I have to stress that 1 hour talk cannot substitute a good reading of a paper or of a book, okay? So don't expect that this talk is a substitution of that. That it is just an introduction just to make it easier to go into this reading. So please do it. And for magnetic structure symmetry and analysis, I think I should recommend, of course, one where I am co-author, that it is this one here from 2015, I think, where you will find practically everything that I'm going to talk today, okay? And in much more detail and much more better explained and with more examples and so on. So, and I have also to say that I'm going to work mostly on most of the things that I'm going to talk about are not only symmetry and its applications and when you are going to determine a magnetic structure, but about the tools and the programs that you have available in the Bilbao Crystallographic server. There is a section only for magnetic symmetry and applications, and we are going to talk not all the programs because there are many, but some of them will be explained or at least shown in this talk and the next one after the pause. And in this section, there are many documentation that you can also complete the talk. I mean, There are several tutorials that are indicated there about explaining with examples some of the programs. Some of the oldest tutorials that of these two programs, MaxMan and K-subgroup they are not fully updated, but the most modern ones are these 3 tutorials that involve most of the programs, not all of them. And again, these are much more complete and much more detailed than what I'm going to talk here. So let me start by something very simple. How do we describe a non-magnetic structure, a commensurate one? And I took this example, lanthanum manganate. It is orthorhombic, and here you see what do we need to report this this ordinary structure. We just say what is the space group, what is the unit cell, and we list the positions of a set of atoms that we call the asymmetric unit. We call it the asymmetric unit because from this set of atoms we are able to construct the whole crystal and to know where are the atoms in space, let's say in an infinite space, because you know that mathematically we consider the crystals infinite. And what does it mean that we say space group PNMA? It means that we know that by using this set of operations, which are indicated in this way, we are going to construct or to produce the positions not only of these only 4 atoms, but of any atom in the space, okay? So if we say lanthanum 1 is at this position, and just by taking this XY set and applying these operations, we obtain 8 lanthanum positions, not only 1. And then we apply the unit cell periodicity, and we know that not only these 8 positions, but also some other ones, which, by the way, we will get not 8 positions, we will get 4, because some of these operations will go into the same position. That we say that the multiplicity of this position is 4 and not 8, because a couple of operations do the same thing on the position because of this special value of 0.25, which say that lanthanum lies in a special position. So, this is just a cartoon showing what we mean by what I just said. Just from these 4 set of atoms, we apply what we say the space group operations, that is this set of operations here. We apply it, which means we rotate X, Y, Z according to a matrix 3 by 3, which is indicated by these symbols, and we add a translation, which is this plus 1/2 for X. For instance, here, in the case only of Y, we add 1/2, and we obtain a new position and a new atom. In the what we call size notation, we just, instead of putting this operation in this way, we do it by indicating the rotation. Saying, for instance, here is 2x, means a rotation, a binary rotation along one axis in the direction x, and then this translation 1/2, 1/2, 1/2. It is clear this, it is very important, because if we don't have this, we cannot go much very further. Now what I want to stress is that these geometrical relations, we are saying, okay, just give me one atom, and if you tell me what is the space group, I can construct from this atomic position, I can construct all the atomic positions which we say are symmetry equivalent. They are symmetry equivalent because I can obtain it from this one by applying these operations and by applying the lattice translations which are defined by the unit cell. Because the unit cell is just telling me everything is repeated according to these A, B, C vectors defined by the unit cell, which defines the lattice. Then, it is not only this geometric property, because you see I said that lanthanum is in a special position. The 0.25 is forced by symmetry. It cannot be 0.25 or 0.25 something. It is just 0.25, and if it just changed from this value, then it means you are in a different physical phase, not in the one you are saying. I'm just, again, stressing it here. For instance, if you see the zero is very, the X component is very close to zero, but it is not exactly zero. And the Z component is also very close to zero and not exactly zero. But this one is exactly 0.25. And why is 0.25? Because I said that some operations just keep this 0.25 equal. I mean, there are two operations of the space group that keep this atomic position the same. So there is one operation that if this would deviate from 0.25, it would mean that instead of having a single atom, you will have one and a double. The orbit, what we call the orbit of atoms, instead of being 4, that I said, will be 8. So suddenly you have more atoms than you should if you still say that your space group is the same one. So what I'm saying is that if lanthanum deviates from this 0.25, it means that you are breaking the symmetry, and the symmetry of the system is not anymore PNMA. Okay? So it means that when we assign some symmetry to a material, we are not assigning only geometrical properties or geometrical relations. We are assigning some property which is a physical property, in the sense that it does not change except if you have a phase transition. So, and this, I continue with this stress that the change of a symmetry of a crystal necessarily implies a phase transition. Not the other way around. I mean, you can have phase transitions without change of symmetry. But if you have a change of symmetry, you have a phase transition. And what do we use for defining these space group operations? We use rotations, translations, and space inversion. The famous inversion that when we apply a space inversion plus a rotation, this we call improper rotation. So we have proper rotations and improper rotations if they are constructed by applying a rotation and inversion. And these operations keep the crystal undistinguishable. You apply this operation and the result is something that you cannot distinguish from what you had before the application of this operation. But and this is the geometrical property that they have, but they have something which is only physical, which is what? Translations, rotations, space inversion keep the energy invariant of any system. It does not require that they keep it undistinguishable, and then it means it does not belong to the symmetry group of your crystal. But the set of operations that we call it the symmetry group of my system is a subgroup, a subset of the operations that keep the energy invariant. And this is very important because this is what ensures that this symmetry group is kept within the whole phase. And if it is broken, it means a phase transition. And the point is that the time reversal operation is also something which keeps the energy invariant. If you go to a Hamiltonian and you apply time inversion, which is changing anything that depends on time and in reverse, then the energy does not change in the Hamiltonian. And this implies for the spins, for our purposes, that is just macroscopically what are the spins or the magnetic moments. If you inverse time, you will change the directions of the moments. And that's what we had all the time. But the point is that time inversion does not appear when we go into magnetic structures, that it is what one gets the impression when one talks about magnetic structures, because suddenly we start to talking about time reversal. No, time reversal is present as symmetry and all the time in ordinary non-magnetic structures. If you apply time inversion, the system is undistinguishable from and it keeps the energy, okay? So it is part of the symmetry of your non-magnetic structure. But we don't use it. We don't use it because all the structures that do not have magnetic ordering have time inversion, is all the time present there. So we talk about space groups, and in a space group, there is the time reversal operation does not appear at all. But it does not mean that it does not exist. It is there, but we don't use it, and we forget about it. Now, when magnetic ordering appears, then time inversion is broken. It does not anymore is not anymore present in your structure. And it is then that we start to talking about time reversal. Because not because it is kept or it is part of the symmetry of your system, it is part of the symmetry of your system when it is combined with something else, with another operation. And that's the big paradox, that when we go into magnetic space groups, we are not adding operations, we are subtracting operations from the original symmetry that had my paramagnetic structure, which was not magnetically ordered. So time reversal is detected when it does not exist, and it is detected in magnetic structures. So, and this is what can be summarized in the case of our example of this PNMA lanthanum manganate. This is mathematically what I just said. I said the symmetry of my manganate when it is in the paramagnetic phase where there are no spins, no magnetic moments, it is not the space group that we are used to use. It is this plus all the operations of this space group multiplied by time reversal. Time reversal, this is a notation, conventional notation. We put it 1' as time reversal, and the translation is 0, okay? There is just, and what is the meaning of this operation? We just go to our structure and just switch the signs of all the magnetic moments that the magnetic structure has. That's what we have to know about what time reversal does in a magnetic structure, just switching the orientation of all the spins. Then, this mathematical equation means this for the operations. These were the operations that we had for PNMA, and they are indicated in black. And now we put a +1 here explicitly to indicate that it does not include time reversal. And then the same operations in space, that means rotation, translation, plus time reversal, these are the ones which are here in red. And this is the full symmetry of the structure in the paramagnetic phase. Again, a question of notation. This was the notation for, the sites notation for a space group operation, R for the rotation, T for translation, and we just extend this notation by including a prime if it includes time reversal, or alternatively we can use a theta, a symbol here, which can be +1 or -1, +1 or -1, to indicate if time reversal is included in the operation. So, now we go to what really happens in lanthanum manganate when you decrease the temperature. It goes into a magnetically ordered structure, which is of this type here, which is collinear along the A direction. And the question is, what of these operations survive? What are disappear and what survive? The one that we know for sure disappears is which one? Which one? Time reversal. Time reversal, which just switches the spins. It's not anymore a symmetry operation. Why? Because when you switch the spins, the system is distinguishable. You have the two situations. Please distinguish what is to make this undistinguishable and to keep the energy. The energy is kept when you switch the spins from plus to minus, okay? The energy is the same. In fact, you have two domains of the structure, one for plus and one for minus. But it is not anymore a part of the symmetry group of the system. So we know this operation has disappeared. But what happens with the rest? Some of them will be kept and some of them will disappear. Which ones they disappear? In order to know that, we have to come back to what was explained this morning, that how an operation, a rotation, proper or improper, acts on a magnetic moment. Because we have to know what is going to happen to the spins when we apply the operation RT, rotation plus translation. And the property is indicated there mathematically. The magnetic moments are axial vectors. That means that when you apply a rotation, then it goes like a rotation multiplied by the determinant of R, or determinant of this operation. That means that when you apply a mirror plane, it is the same as if you applied a binary axis perpendicular to the plane, because you multiply by the determinant of this mirror plane, which is -1, and in fact, you go into the matrix of a rotation. So you could say it in another way, saying that magnetic moments always rotate by means of proper rotations. Even if the R is an improper rotation, as it is multiplied by its determinant, then it becomes a proper rotation. And but so this is what we have to do. We just go to an atom with a mirror and we apply the operation with time reversal or not time reversal, and we obtain. And remember, if there is time reversal, then the operation will be determinant of R and multiplied by theta. Theta is -1 if time reversal is included. So you have the -1 of time reversal, maybe the -1 of the determinant if it is an improper rotation, and then it will become a proper one. So by this means, all these operations disappear, because one can just make the calculation and see that there is no way. If this is fulfilled, then the one that switches, it is this one, but with time reversal, this disappears. If this survives, this disappears. If this survives, then this one has to disappear. Okay? Because the difference is only a change of sign of the spins. So, and this is the summary. I mean, from all the 16 operations, we have 4 which are red, that means that are with time reversal, and 4 which are black, which are without time reversal. And this is what we call Pn prime Ma prime. Why? Because these 2 operations, the mirror plane N and the mirror plane A, are primed, are the ones which are here listed here below. If we go to the Bilbao server, that we can do, you have your computer, you can do it yourself also. You just go to this first program, which is only just a database of all the space groups, magnetic space groups. So I go here, and I go to the PNMA. PNMA is 62 is here. And here you have the list that was shown this morning about all the possible magnetic space groups coming from PNMA. And the one we are talking about is here, okay? This is the one, we have it here. So we have chosen the 62.448, and here you have the list that I'm just showing. This is just to show you that you can easily consult any magnetic space group once you know the label, or even only the starting space group. So, and what is the structure of this magnetic space group? The structure, all these operations which are black do not have time reversal. And if you multiply one by the other, you don't go into a red one, okay? Time reversal does not create by itself just multiplying operations that do not include time reversal. So all these operations form a group, a space group, and this space group is monoclinic. It's this one which is indicated here. And all these red operations here, if you multiply one operation which is red by one which is red, that means that the red is only just used in our server. I mean, You will not see it in generally. It means only that it is time reversal. It is included in the symbol just by the -1 that you have it there. So if you just take and you multiply two operations which have time reversal, the result is what? An operation with time reversal or without time reversal? Anybody knows that? If you multiply an operation with time reversal, which means switching the spins once, and then you multiply by another operation which again switches the spins again, what is the result? An operation with time reversal or without time reversal? Without, okay? So it's always one of the black here, except for a lattice translation, maybe also includes some lattice translation, but it will be one of these 4 plus a lattice translation. That means that these operations with time reversal, they never form a group. They cannot, okay? So, but one can demonstrate that you have that this group is the monoclinic group formed by these operations plus this group, again, multiply by one of them, by one of these operations that we can take, for instance, the first one. That is the one that I took here, okay? And so this is what in mathematics is said a coset decomposition. We are decomposing the group in 2 cosets. This is the first coset, which is always a group, and this is the second coset, which is not a group. Okay, so let's go back then here. So this is one of the types of magnetic space groups that you can find in your structure. But there are other 2 types that you can find. And these are just listed here. The one that we talked about is this one here, what we call type 3. It is a group without time reversal, multiply by the same group, multiply by an operation. So this coset is just all the operations of F, all of them multiplied by this operation here. And the other type is type 1, which the one which is type 1 means that you don't have time reversal, but you also do not have time reversal combined with something else. This is a very special type of magnetic space group. And we will see that the notation is a little bit confusing, the traditional one for these magnetic space groups. And type 4, it is similar to this one, but of a very different type, because here it is time reversal, while here not, okay? And here it is not indicated, but it is not, it cannot be time reversal. If it's time reversal plus a translation, this is what we call type 4. This type of operation, which includes time reversal plus a translation, we call them anti-translations, okay? Because it means that you have an operation which is, you translate, and then you switch the spins of sign, okay? And this is type 3, type 4, and type 1. What are the type 2? The type 2, we already know them because they were the ones for the paramagnetic structure. They are the ones which are of this type. A group and the same group multiply by time reversal. That means what we call the gray groups, the ones that can only be associated with non-magnetic structures, with paramagnetic ones, or even with diamagnetic ones. So, tables of magnetic space groups in what we call the standard setting, you can find in this very nice book of Litvin, that it is freely available in internet with nice pictures and so on, where the listing of the magnetic space groups are given in what we call the Opekowski what? Opekowski-Guccione setting, and then you have the listings which are also can be downloaded and in digital form of Stokes and Branton Campbell in the web page, isotropy web page, or what you call it, isotropy suite. No, what is suite? Okay, isotropy software suite, and you can find it there very nicely. And then you can find them in the way that I showed you before in this web page in the Bilbao server. And I must say the listing, it is very nicely put and so on, but it comes from the digital files that we provided by the isotropy software suite. So an important point is that there are two ways to describe the magnetic space group, the BNS and the Opekowski-Guccione and the BNS, which is, what is BNS? It means what? Okay, that's so it's the name of the co-authors of the first paper which produced the first listing in this way. And the point is that the difference between the two is that the OJ setting describes the operations not using the actual unit cell that describes the periodicity of the structure of the spins, and therefore it is more difficult to apply with usual crystallographic programs. And the software which is available up to now, to my knowledge, it's only for the BNS setting, for the BNS description of the magnetic space groups. And therefore, from now on, I will only talk about magnetic space groups using what we call the BNS setting, and the standard, when we call the standard description of a magnetic space group, it refers to these BNS listings. Recently, we were so daring to propose a new symbols for the magnetic space groups in 22, because we found that the traditional symbols had some problems and led to some wrong conclusions by even experts. And so, and very recently in 24, in Acta Cris B, by the way, we are publishing a special issue on magnetic structures, and one of the papers is the one that you can see here, where in a very brief way you can read again, and you will about the structure of the magnetic space groups, about these four types that we have described, and also about these unisymbols, which are new and which pretend to unify and to go beyond this famous splitting between BNS and OG symbols. So here you have the listing of the magnetic space group for a type 1. You see all the operations are black. That means there is no operation with time reversal. And it is in fact, the listing corresponds to the same one that you will have in the ordinary space group PNMA, okay? So the operations are the same. And traditionally, people use exactly the same symbol, just saying, okay, my magnetic space group is PNMA. But to say my magnetic space group is PNMA is not the same thing as saying my space group is PNMA. Why? Because if you say it is my magnetic space group, you are saying explicitly that there is no time reversal in these operations. While if you are saying PNMA for a paramagnetic structure, implicitly these operations have +1 and -1. I mean, time reversal is included, even if you don't talk about it. So that's why in this new uni symbol we use to indicate that it is not an ordinary space group, that it is really a magnetic space group, and it does not include time reversal, then we put .1, okay? Then this is the other one that we already saw. No, this is a type 4. A type 4, we said it is one that has an anti-translation, okay? So this is the group which is black, which is PMN21. And this one multiplied by an anti-translation, you get the new, the magnetic space group. And the magnetic space group in the old or the traditional notation would be like this, PB. This B here indicates this anti-translation. And this morning you have shown that PB corresponds to one of these black and white lattice that were described, okay? When we use this type of approach, we don't need, if you were scared this morning about so many black and white lattices, you can be tranquil, you don't need to use them anymore, because when we use magnetic space group, nobody is going to ask you what is the black-white lattice of your magnetic structure. It's going to ask you what is the magnetic space group of your structure, okay? No, you don't need to have in your memory all these black and white lattices. You only have to know if your system has an anti-translation or not, and this is indicated in the traditional way here as part of the lattice, like a black and white lattice, but in this uni notation, we indicate this anti-translation here as part of the point group that has the magnetic space group. So it is clearly indicated that you have 1' sub B. That means that you have this anti-translation as part of your magnetic space group. So, and now we come to the point, how do we describe now a magnetic structure in a very standard form, which can be transported, which is portable, and can be done in a similar way as we do with ordinary crystallographic structures. And the way is very simple and very obvious. You just have to use the magnetic space group. You have unit cell, okay, asymmetric unit indicating the atomic positions of the asymmetric unit, and then the difference with the description of an ordinary structure is that you have to add also a list for the asymmetric unit of the magnetic moments, okay? As there is only a single magnetic atom in the asymmetric unit, you only have to put, okay, my manganese, which is at this position, then it has this magnetic moment. And it is important to indicate also what is the constraints that symmetry give you to this magnetic moment. Here we indicate that this zero and this zero, even if experimentally are zero, from the symmetric point of view, from the symmetry point of view, they are not forced to be zero, okay? So it's not like the 0.25 that we spoke before for the atomic position of lanthanum. This zero is zero because it is observed to be zero, but if it were different from zero, we will not break the symmetry. It is allowed by symmetry that there can be some counting of the spins. And in the same way that we had the list of positions of symmetry operations of the group, again, we have the list of symmetry operations of the magnetic space group. And only from this information, we can construct the whole magnetic structure, because the operations of the magnetic space group, we can apply to these atoms and these magnetic moments, and we can construct and produce the magnetic moments and the positions of all the atoms in the whole space. In the same way that we have in ordinary crystallography Weikov positions, we have Weikov positions for the magnetic space groups. And in our particular example, the manganese, it is in this particular orbit, Weikov orbit, which is, we said, multiplicity 4, only 4 positions in the unit cell. And what else? As you see, to indicate the orbit, we only indicate not only the positions of the 4 symmetry-related atoms, but also we indicate the symmetry relation of the magnetic moments. Okay? For me, it's very difficult to see it in this, but you will see that when you go from the first position to the second, then mx changes sign, my does not change, mz does not change. Okay? And that's the symmetry relation between the magnetic moments. How do we know that this is happening? This is just a consequence of the general set of these operations. So in fact, this is what is given me for this particular Weikov orbit for manganese, that along X, Y, or Z, you have these types of arrangements which are different, and they have in the traditional literature, they are called A, F, or G. But look, imagine that lanthanum were magnetic, and you see that if lanthanum had a magnetic moment, then it will be forced by symmetry that the magnetic moment could only be along Y, and it will be forced to be zero along X and along Z. And this is part of the symmetry conditions, symmetry constraints of the magnetic space group, in the same way that in ordinary space groups you have it for coordinates. Once we know that we can describe magnetic structures in this way, then the natural thing was to generalize the format, the SIF format that is usually in crystallography for for communicating ordinary structures, just to generalize to magnetic structures. This was done already a few years ago and promoted by the International Union of Crystallography and headed by Branton Campbell, who was at the time chair of the Commission of Magnetic Structures of the International Union. And happily, after a few years and a lot of paperwork and fighting with what is the name of this commission? The COMFIPS Commission of the International Union. It was officially approved, a format that in principle should be the standard for producing these magnetic zip files. And here you have an example for not for lanthanum manganese, but for another perovskite. But again, looks like if you see a zip file of an ordinary magnetic structure, you will see that this type of information is just the same, except that for the space group, instead of a space group, you have the list of operations of the magnetic space group. You can distinguish that it is a magnetic space group because you have the +1 and -1, which do not appear in ordinary operations of space groups, but the unit cell is just the same. And then the asymmetric unit for positions is just the same. And then you have, in addition, a loop to indicate the magnetic moments. Okay, and that's it. The point is that these massive magnetic zip files can be also used for incommensurate structure as long as you use superspace groups that will be talked in this workshop later during the week. Here again you see how we describe this magnetic structure of this perovskite just by unit cell, asymmetric unit of position, asymmetric unit of magnetic moments, and list of operations of the magnetic space group. And this is enough. You can take this and you can transport it into very different software programs, like for visualizing in Vesta, for visualizing in JMOL, for visualizing in our server, in the Bilbao server, or for editing in the isotropy software suite, and so on and so on. So let me again show you something. Let's practice a little bit. How much time? So 4 minutes, no? Something like this. So, okay, so let's play a little bit. If you have your computers and you have access to the Bilbao server, you could go to this program, which is called Identify Magnetic Group. Okay. So this is the program here, okay? Identify magnetic group. And what does this program? This program, you can go into one of these zip files. For instance, I could go here and just take these operations here. In fact, you only need to put the set of generators, and the list in the zip files is complete. But the program can work only if you does not need all. If you put all, of course, it's okay, but the only thing is that you have to put a minimum set that just by multiplying ones with the others, you can construct all of them. Well, and I just submit. And now the result, you can see it here, just identify this group. But want to put it in standard form. Structure is type on a standard set. In ordinary crystallography, it is not usual to work in non-standard settings. Normally, even if you have a phase transition from, let's say, hexagonal to orthorhombic, and you are in the orthorhombic phase, you go to the orthorhombic unit cell and you describe your orthorhombic phase in the standard setting of this space group. In magnetic structures, is not. It could be done, and but the point is that we have started to use magnetic space groups. Okay, so people are used to work with the image of the paramagnetic structure, and they don't want to go into a description which is not related with these paramagnetic structures in an obvious way. So in most cases, if you go to the database, MagData, where we have about more than 2,000 structures, the usual way that we have introduced the structures is in a non-standard way, because otherwise you lose the reference to the parent, to the paramagnetic structure. And because you see here, you have to do not only a change of unit cell of ABC, but you have also to change the origin. And sometimes if you change the origin in a structure, you get lost about how you describe the structure. So, but it is the case here that if I want to show my structure in this nice way here, like here, then I have to use a non-standard setting of the magnetic space group. And what does it mean, this matrix, which represents the transformation? Well, this matrix, I will explain it just now. Coming back to the presentation. So this is the result we have obtained here. And this is the transformation, which is a 3x3 matrix, which I call P, large P, a translation which is the small p, and the interpretation of that is indicated here. The last column, small p, is the origin translation with respect using ABC of the unit cell that you are using. And each column of this 3x3 matrix is indicating the new A, the new B, and the new C that you have to use in order to produce, to have your magnetic space group in a standard form. And what does it mean in a standard form? It means that this is the one that you are using, these are the operations that you are using, and you see here, for instance, there is 1/4. 1/4 normally in a standard setting will not appear for something which is, in this case, orthorhombic. And this will disappear by this transformation, which you can put in this way, or even it is much nicer or much shorter, just if you put this is minus B, A, C. So this is the new unit cell interchanging the cell parameters, and then this is the translation of the origin. And this is again what it happens if you do that, is that the set of operations become the same ones that you will obtain in these listings that I told you before, okay? The ones that you can consult in internet from the isotropies software suite or from our Bilbao server. And just for reference, so that you can keep it, how do you do this transformation? You do it by means of this matrix algebra, okay? This is the new R prime T prime, applying the PP that we said is the transformation that it was indicated here. Here in between is the non-transform operations, and here again the PP, here inverted and here. And of course you can switch from one to the other just by inverting the equation. And the positions, of course, you have also, if you change the unit cell and the origin, the positions of the atoms will change. And they change according to this equation here. And the magnetic moments also change according to this equation here. So this is all that you keep it for you for reference if you want to do it by hand sometimes. But you have in the Bilbao server, in some other ways, in the tools to do this automatically. So now we can go to consequences of symmetry. And now we know how we describe a magnetic structure with symmetry. That means with its magnetic space group. By the way, I never talk about it, but I'm talking about magnetic space groups, but people also call them Shubnikov groups, okay? So it is the same thing. Of course, some people like them to be called Shubnikov groups, especially if you are Russian or close to Russia, and they have, of course, reasons for doing that. But I like them. I like to call them magnetic space groups because if I call them Shubnikov groups, I would also call space groups Fedorov groups because they are also coming from Fedorov. So, well, now the point is how we have seen that magnetic space groups are very useful just to simplify and to standardize the way to describe a commensurate magnetic structure. But not only that, a magnetic space group means that if you know it, you know all the symmetry constraints of anything on your structure. Because the von Neumann principle says anything that is allowed in your system will have to comply with this magnetic space group. The tensor properties, for instance, will be constrained by this symmetry, in particular by the magnetic point group that comes from this magnetic space group. And reversely, anything that is allowed by this symmetry, maybe you don't detect it because it's very small, but it is not forbidden by symmetry, so it could be there. For instance, systems where you have small cantings like weak ferromagnetism that normally by neutrons is not, cannot be observed, But you know from the symmetry, from the magnetic space group, that this system must have or can have weak ferromagnetism, even if you don't detect it because it's too small. But if you go to the laboratory and you make, instead of neutron experiment, a macroscopic measurement of magnetization, probably you will see this small component of weak ferromagnetism, and which was already suspected only from the point of view of symmetry. You have in the Bilbao server a very useful program, which is M-tensor, where you can, once you know your magnetic space group, you can go there and this is the main page where you have all kinds of tensors that you can investigate, from equilibrium ones, optical tensors, nonlinear optical properties, and transport tensors like Hall effect and things like that. And again, here there is, if you are interested in this program, the best thing is that you go to the original paper where the program is explained in detail with many examples. But just to show you how it works, we can go again to the one of these programs. We were in identify, we go back and we go to M-tensor, okay? M-tensor, we are here, and we are going to equilibrium tensors. And here you have quite a lot divided in blocks, because many of them have the same transformation properties. So the constraints of the symmetry are the same for all of them. So, but what is the example that I put here? I think it was, yeah, magnetoelectric tensor. Okay, so magnetoelectric tensor is here. Let's, so you see here, magnetoelectric tensor, you have direct effect and inverse effect. One is magnetization produced by an electric field, and the inverse one, polarization produced by a magnetic field. Okay, so they are related. One is the transverse of the other. So, and it is indicated by a matrix alpha. So I just go here, and one possibility would be you go here and you put your space group number, or you choose it from the list here, okay? Again, you could put the point group, or you could go to the list of the magnetic space groups. The tensor constraints, symmetry constraints, only depend on the point group. Why we put also the input for space groups is because sometimes the point group is in the space group is orientated in a different way than in the standard way for the point group. I mean, for instance, you may have MM2 or M2M, and the results will be different. So, but so here you go to your group or your point group, and you see what are the but in our case, I mean, there is another possibility, which is you can go and click here, say, show symmetry adapted tensor for all the magnetic point groups in a standard setting. I click here, I go again to equilibrium, and I go again to my then this list are the point groups that have forbidden this magnetoelectric tensor. It's 0. And these are the ones which, as you increase the symmetry, of course, the number of possibilities in the tensor decreases, and you have very different possibilities, okay? Depending on your point group symmetry. And you know which point symmetries allow a magnetoelectricity and which ones not. By the way, it's linear magnetoelectricity, of course, will be different if it is a quadratic response and not linear. So let's come back to the presentation here. And so this is what I show you. And here we go to another perovskite again, which is in the database. You have the two entries for this phase with very different magnetic space groups. It is the same magnetic phase, so one of them should be wrong, okay? By the way, the database that you have, this MagData entry there does not mean that the structure is correct. It may be completely false. The only condition to be in the database is that it is a structure that has been published, and it has been published with enough information and enough clear information that we could transport it into a description using the magnetic space group. Because most of the structures, especially in the old times, they did not use magnetic space group symmetry. So once you have the paper, then you have to translate it and to interpret it and to see what is the magnetic space group and describe it in this way. So the point is that the difference between these two arrangements, you will see it is the same arrangement, but only orientated in a different direction with respect to the unit cell. In one case it's along C, and in the other case it's along A. And this makes the difference. This makes the difference that in one case is of this type and this type. Two different magnetic space groups. If you go to the tensors for magnetoelectricity, you see they are quite different. In one case, the response is linear. I mean, you apply a magnetic field along X and you will get polarization along X, while in the other case, you apply a magnetic field along Z and you get polarization along X. So from this point of view, if you had a single crystal and you made a measurement, you could distinguish between the two possibilities and the two arrangements quite easily. The reason why there are these two entries for the same magnetic phase is because the system is pseudo-tetragonal, because it comes from the perovskite. And being pseudo-tetragonal and being an experiment with powder practically is very, very difficult to distinguish if the spins are oriented along X or along Z, okay? In this, but what I want to stress then is that by means of other experiments, and if you are lucky to have single crystals, then you can distinguish. Also here I want to show two cases of two very similar structures, but one has a magnetic space group which is of the type 3 and which allows magnetization along one axis, which in fact is the B axis, and which is weak ferromagnet, and it is reported to be weak ferromagnet. And this other one, which has exactly the same spin arrangement, it is of type 4, and it is, in fact, the point group is for type 4. I didn't stress it, but all type 4 magnetic space groups, the point groups are gray. And if they are gray, it means that they cannot have anything which is not allowed also in a paramagnetic structure, okay? Because a great point group is the point groups that have also paramagnetic phases. I like always to speak about this this nice system. A long time ago, in 2010, it was published, this paper, where they have a magnetic structure where the arrangement was either of this type or either of this type. So the difference only differ exactly in the same way that in the previous example, only in the orientation of the spins. And the reason again is because the system is tetragonal and one cannot distinguish the orientation. And in fact, but what they knew is that this system had some weak ferromagnetism perpendicular to the orientation of the spins. Okay, so it could have some canting, ferromagnetic canting of the spins. And this allowed then, thus by applying a magnetic field, which would be coupled to this small ferromagnetic component, just by rotating the magnetic field, one could just rotate the orientation of the spins. That means it doesn't matter that we don't know the orientation of the spins. We can just force it by means of a magnetic field. If I apply a magnetic field, the weak component will be aligned with the magnetic field, and therefore the orientation of the antiferromagnetic arrangement will be perpendicular to the magnetic field applied. And that's what they did. And so they did that they just rotated the magnetic field, or probably in the lab what they could do is just to rotate the sample and just keep the magnetic field. And by this way, they just manage to, and then they measure the polarization of the sample. It was a single crystal. So they measure the polarization as a function of this rotation of the field with respect to the sample. And this is what they observe. They observe that by some angles, the polarization, there was a spontaneous polarization in the system. We were not applying an electric field. They were only just applying the magnetic field. And they got this polarization along Z. Z is the tetragonal axis, so perpendicular to the plane of the spins. And while PA was practically zero all the time. And the point is that they tried to explain what was happening by means of a microscopic mechanism. I don't remember exactly which one. But the point is that if you take the magnetic space groups that correspond to one orientation and the other, then the reason it is really clear. Because for this orientation, then the group is this one here, which does not allow, wait a moment, no, this allow some moment along B, which is this one here, and no, we are talking about depolarization, okay, not the magnetization. So this group is non-polar, okay? So when the system is in this arrangement, then the system cannot have a spontaneous polarization. So we are at these points here. And when the system is in this orientation, then the magnetic space group is this one here, and this one is polar, and it's polar along these two axes. And these two axes, if you go to the transformation to standard, is the z-axis. Okay, so you have a polarization allowed by the group, by the symmetry group, and that's what you are observing. So if you just rotate the magnetic field, you are rotating the orientation of the spins, and then you are observing P for some orientation, and then P0 for some other orientation, and so on. Well, and then you have this tutorial here that you can, practically everything that I've talked today in this lecture, you can see in much more detail. And I think with this, I can finish this first part. Oh.
Okay, thank you very much. So now the lecture, some question, open to the question.
Oh, the M-tensor package. You had some notation that I thought was very interesting with the A, E, V squared, all of this stuff. How can I understand that notation?
Yeah, this is a very old notation for tensor properties. It comes from the 40s, from a paper by somebody called Young. So we call it Young symbols. And it is very simple. If something transforms according to a polar vector, it is V, okay? If it's just a tensor of rank 2, which is transforms according to the product of two polar vectors, and it's symmetrized, like for instance, yes. But I think here you don't, yeah, you have it here. Yeah, here is A, E, B square, okay? Why is B square? Because the transformation here, you have two vectors, P and H. But H is axial and P is polar. That means if you have an axial vector, the symbol is A times V. And if you have a polar vector, which is P, then it's V normal. And then it is, if you change for time reversal, the tensor is odd, because H, if you change time reversal, H should change to minus H. And that's why the Chance symbol for this tensor is AE V square. That's the point. But it's more complicated. You may have antisymmetric V square antisymmetric, V square symmetric, depending on the tensor and so on.
Yeah, I have a question. So the magnetic C file contains all the information also about the space group, not only the magnetic part, also about the crystal structure.
Yes.
So for example, if I set all the magnetic moment to 0, it then goes to the Just the crystal structure?
If you put all the magnetic moments to zero, yes, you will get
just the crystal structure.
A crystal structure, yes, yes.
So if we have the magnetifier, so we don't need C5 anymore.
But you will have probably a magnetic, an ordinary structure, which is described in a space group or with a less symmetry that it has. Because normally, when you go into the magnetic phase, in the magnetic structure, some operations of the parent space group disappear. And some atoms have split it. And so your asymmetric unit in this magnetic C file will have, in many cases, atoms which are symmetry related between them in the parent phase.
I see. So we lost some of the symmetry. Yeah,
yes, you always lose some symmetry, but in the case of the simple examples that I've shown, PNMA and so on, it is a k equals 0 with propagation vector 0, so the unit cell is the same, and you don't lose any parent space operation. But in many cases, for instance, if you are in a tetragonal structure and your atoms, your spins are on the plane and are collinear in one direction, then you are losing the tetragonal operation necessarily. And then your magnetic C file, the atoms which were related by the fourfold rotation will be splitted. They will be there. So, but in principle, you have isosif is a very nice tool of the isotropy software. You just put the maxi file there. I mean, read the maxi file. There is an option saying remove the magnetic atom, the magnetic moments, and it does it, okay? And then you have a button saying detect high symmetry, and then it will tell you, okay, it will go to your real structure. Why this happens? Because normally the magnetostructural effects are too weak, so you don't see this splitting of the atoms, which formally can exist. You cannot see it because it depends on the spin-orbit coupling, which is very weak. And so in principle, that's the reason why in not all cases, I will show you in the database that there are several cases where you have these famous structural transitions which are observed at the same time that the magnetic structure, and they are not really a different transition. It's just that the magnetostructural effect is so strong that you see this distortion of the atoms in the structure.
So we can continue.
There is a question.
Yes, thank you for a nice talk. I have one question about the magnetic subgroups. Like for the PMMA, you mentioned it have 8 subgroups, right? The magnetic subgroup for PMMA. Yes. Yet, does that mean with any K vector, the magnetic structure should be in these 8 subgroups?
Well, if I understood your question, the question of what are the subgroups that one has to consider for a given space group, I haven't talked yet about this. I mean, that's this listing that appears when you have to choose PNMA and you have a listing. These are in fact not subgroups in the sense that there are other tools that I explain in my next talk where you say, okay, this is my propagation vector. Okay. What are the subgroups that can happen? But it's not here. Here, it's only just a mathematical trick saying, okay, what are the magnetic space groups that have the same PNMA as what we call the root space group. And all these magnetic space group have in the number, they have 62 because 62 is the number of PNMA in the international tables. And then you have 62 plus some number just to indicate what is the magnetic space group. But this does not mean that you are assuming some kind of group-subgroup relation, which in many cases exists, and, but the real group-subgroup relation will be with respect to the paramagnetic space group, and this paramagnetic space group may have nothing to do with the PNMA, maybe a completely, maybe a tetragonal. You may go from a tetragonal parent phase to a magnetic space group which has PNMA in the label.
Okay, thanks. I understand.
We can continue, but shall we have a 5 minutes break? Or?
Yes. There is no coffee or something? No?
Coffee, not, probably not after next.
Huh?
1 hour later.
Okay.
So I think probably 5 minutes break for after that continue. So no coffee there, but maybe you can go to toilet or just a rest. So after 5 minutes, maybe how about the 3:40 we will start. Okay.
I still haven't sent the
4点半。
你有那个时间表？
Describe in detail. But and again, the tutorials that I mentioned before, I'm going to concentrate mostly now in what you can find in these tutorials. Although I have some examples that are not in there. And in principle, you have, I don't know, we have very little time, but I also, you have to have available a set of zip files, okay, that I put in some place and that you can find, no? Do you have it, do you know where they are? Yes?
Anyone who has problems with tested cause, let me know right now.
Are we all okay? Should we proceed? Okay.
It's okay? Yes. Okay. Okay, so let's start from the beginning. The question that the programs in the server can help you are just mathematical ones, have nothing to do with your experimental data, except the famous propagation vector of vectors, okay? So, and here's what I said. My question that I want to answer is which M magnetic space groups are possible for a magnetic structure having a space group PNMA in the paramagnetic phase if the magnetic ordering has a propagation vector 1/2, 0, 0. From what I know that the propagation vector is 1/2, 0, 0, because I have done some diffraction experiment and I started to see in my diffraction pattern some peaks which I cannot index with the lattice of the ordinary paramagnetic unit cell, and I have to index them just by means of 1/2 with respect to the reciprocal lattice A star of the parent unit cell. What is the idea of the propagation vector? The propagation vector is a wave vector. It's just indicating me that my magnetic ordering is according to a wave where its wave vector is 1/2, 0, 0, 0. That means that if I have a wave in my crystal, which is according to this 1/2 A star, in my diffraction of the magnetic scattering, I will see that Bragg peaks according to this K vector, okay? This is not so simple as that, as Dimitri and other speakers will explain, to find out in your data which is the K vector or K vectors which are involved. It's not, it's the first question that you have to answer, and sometimes it is not so easy. Normally, because the solution is not a single one, you may have very few ones that can have the same answer. But the point is that to answer to this question is a mathematical problem. Okay, once you know what is your wave vector, then the possible symmetries, it is just a mathematical thing that a program can solve. And for this particular case, that's what you obtain, okay? What is the program doing? The program is doing, saying, okay, if my K vector is this one, the point is that all the lattices that fulfill this thing here will be -1. So my magnetic unit cell will be doubled along the A axis with respect to the paramagnetic unit cell. And I know that if I go into 1/2 of this magnetic cell, that means if I go to the next cell along A of the paramagnetic, the spins should be exactly opposite because of this wave function. And only doing that, you can do the mathematics and you can obtain that all these possibilities. And the point is that you have what we call a group-subgroup structure where one can distinguish 4 maximal symmetries. Of course, there is no theorem telling you that my system should stay in a symmetry corresponding to these 4 possibilities of maximal symmetry, but this is the practice. Empirically, most of the systems just get magnetic orderings according to very high symmetries, corresponding to the wave vectors that you have seen. That's what we call K maximal symmetries, K from the K vector, and this, in this case, will be these 4 here. The other ones, of course, are possible, and they are possible, and if you are not happy with a refinement in one of these 4 possibilities, then you can always go down to lower symmetries. If you go to lower symmetries, it means you have more degrees of freedom in your system. Your magnetic moments will be less symmetry restricted, so you will increase the number of parameters in your model, and maybe you are happy because increasing this number of parameters, then the refinement gets better. In some cases, it gets worse because you have too many parameters and you have to stay in the higher symmetry. So, if you go to the database, about 70% of the structures have this maximal symmetry. So the first guess is to try what we call these K maximal symmetries, and in this particular case, for this compound that we have mentioned already once, it is in fact one of these. And this is the approach that, for instance, I have used to construct the database. I told you that most of the old papers never get worried about identifying the magnetic space group, so you have to start from the scratch. And what I do is just go to the knowledge of the K vectors, go to the knowledge of the paramagnetic structure, try with one of our programs the maximal symmetries and point. Normally, you identify immediately the model that is being reported, and you can identify the magnetic space group that corresponds to the model that has been reported. And that's why we have this program, which is MaxMan, which is maximal magnetic space group for a given space group and a propagation vector. It does not construct and calculate all the possible symmetries, only the maximal ones. And for instance, for this other case, the first thing that one introduces, let me show you, I will not, this is in green, it means that we could just try it, but it means losing a lot of time. So we introduce only the parent space group, okay, which is the one here, then the propagation vector, and nothing else. That's the only thing that you have to include. By the way, you see the propagation vector is 1, 0, 0, okay? And 1, 0, 0 is not a reciprocal lattice vector, okay, in this case. And there are still papers where they get confused about that, and they are not happy when they get a 1, 0, 0. If they see a peak at 1, 0, 0, and in a case like this, they think, okay, this is K0. Okay, and this is not the case here. Why? Because the space group is C-centered, and if it's C-centered, 1, 0, 0 is not a reciprocal lattice vector. It's just in the border of the Brillouin zone, in fact, okay? Because the reciprocal lattice vector along A is 2, 0, 0. So the propagation vector is 1, 0, 0, and then this is the list of maximal symmetries that the program calculates, and it indicates which ones are allowed for my structure, because the system has also, I didn't say it, but you can, it is optional, but you can include a zip file of your initial paramagnetic structure, and then the program tells you, okay, of these 8 maximal symmetries, 4, you can forget about them because they force a magnetic moment 0 in the position where your magnetic atom is. So you can forget about them. Then, and you have only 4 possibilities. And from these 4 possibilities, again, let me just remember this matrix here. What does it mean? I think even you can see it here in probably not no, all the groups are different, but in many cases you may have the symbol of the group is the same here, and the matrix here is different. That means you may have a subgroup of the parent gray group of the paramagnetic phase. You may have the same type of magnetic space group, but oriented in a different way or with a different origin. And these are different subgroups, and which have nothing to do in principle. And they are listed here separately, and the difference between them is only the matrix, the transformation matrix here. This transformation matrix is similar to the one I showed you in my first talk, but there is a very important difference. This matrix is the one that is telling me this subgroup becomes standard for this, the type that I'm putting here for the symbol, if I make this transformation. But I do it with respect to the it is this transformation is respect with the unit cell and origin of the parent paramagnetic space group. While in the case that I was showing you before, it's with respect to the So you see here, for instance, for this case here, this is a definition of a subgroup. You have again the PP transformation to standard, the translation with including an origin translation and so on, the same equation here. Everything is the same, except that you see here there is a 2A here in the transformation. Why? Because it's the unit cell that I'm using for the subgroup. It must be multiplied by 2 along A because it corresponds to a K vector 1/2, 0, 0. And we said the unit cell is duplicated with respect to the parent unit cell. Otherwise, you cannot put the subgroup in the standard setting. So here again, the difference. One thing is describing a group-subgroup relation between the gray group that describes the symmetry of your paramagnetic structure and the magnetic group that describes the symmetry of your magnetic structure. And the transformation requires this doubling of the unit cell. And here is the same thing when you are going to see it in the C file, in the magnetic C file that you are going to construct for this particular structure. You are going to say unit cell used 2A, B, C. So I duplicated already the unit cell with respect to the parent, because otherwise I cannot, you must use a magnetic unit cell, which describes the periodicity of your spin. So you have to duplicate here and to say, okay, I'm using a unit cell where VA is double with respect to the original parent unit cell. And then to describe the transformation of my description to the one of the standard setting of the magnetic space group, it is just the same transformation as here. What is the difference? Instead of 2A, it's a single A, because the duplication is already done in the unit cell that I am using. And here there is 1/8, while there is 1/4, because there the translation of origin is with respect to the original A of the parent phase, while here the translation is with respect to the duplicated unit cell that you already are using in the description of the symmetry operations. So very important to distinguish these two things. And this you can see it in the C files, in these two tags, info tags that you get in the maxi files. One to indicate your duplication of the 2A, your unit cell, which is indicated somewhere here. Okay, so your A here is double with respect to the original parent phase, and then the transformation to standard. So I repeat from here, if you just take these operations and you put them in the program of the Bilbao server, it will give you this transformation here, and not the one that appears in the here. Well, for this compound of these 4 possibilities, this is the one that corresponds to the experimental magnetic structure that is observed. Well, let me do it quickly, because otherwise you will not get much information or feeling of what we are talking about. Let's go here, Max-Mang, okay. This is the input page. I will click here saying the structured data of the paramagnetic phase will be included, okay. if your structure of the paramagnetic phase is in a non-standard setting, you can click here, okay? I think in our case it's in standard, so we will not click it here. Then I put here the, what was the wave vector? 100, no? I think. Yes. Yes, 100 is our propagation vector. I don't put the space group here because it's going to be read from the zip file, okay? But anyway. So the first thing is, as I told the program that I'm going to introduce a parent structure, the first menu is just to look for this parent structure, okay? So I just go to the desktop. Go. Documents. Okay, so here, I think it's this one here, lanthanum copper oxide. You upload, and here is what we said. It is information, complete information of a magnetic structure or an ordinary structure. Asymmetric unit, unit cell, space group. And now we say copper is magnetic, okay? We submit. Is somebody following it by yourself? Yes? Anybody is trying with the zip file that you have available? Nobody is that. Another point is that some of our programs are not what we could say very fast, okay? No, I think the problem is that the programs are not very efficient. They use, in many cases, interpreter codes. So it's, so here we have hopefully the same thing that we said, and let me show which is the good solution. Of course, if you don't know which solution is the one, in your refinement you have to try these 4 possibilities, okay? One by one, refine and see which one you are happy with. But as we know the solution we said is this one here, the second one. Okay, so it is this one. We say show. And now it's telling me, okay, there is still a single, there is no splitting, so I have still a single copper, and the X component is 0 by symmetry, it's forced to be symmetry, and I have free my, m set. And here it gives me the orbit, how this m and y, y and m set will change from one atom to another. So I think the solution will be that my is a long set, okay? So just put here 1. When you start your refinement, you don't care which value you put here. You can just put an approximate value. If you put if you put the 2 coordinates different from 0, of course the system will be non-collinear, okay? But normally you can start by collinear arrangements. If you are not happy, then you can include non-collinear components. And you can just watch how it looks, the solution like this, okay? So that is what it's telling me. And voila, that's, the point is that this is going to work in reality. This is the model that is being reported. And by the way, here, it says BCS file. Now you can just take the file of this model, download it into your folders or into your refinement program, and I think Full Prof can read MC files, Jana can read MC files, Jesus I think also, and you can start from this and try to refine. In principle, you have a single parameter. If you are not happy, you can introduce the other component which is free from symmetry and see if it is needed or not. Yeah, that's what I wanted to show you. The structure which is reported is this way here. And this with these values here, and you see this 0. You see this 0 is not forced by symmetry, while this one it is. Okay, and a very important thing. You have a tutorial of Maxman with another compound with holmium manganese oxygen that you can, and then we can go to K subgroup MAC. K subgroup MAC does combine with MAC modelized, does the same thing as Maxman, but allowing for more than one propagation vector, which is not the case in the previous program, and allowing for symmetries which are not maximal ones, which can happen. And the tutorial where you can see this, how it works with much details, is in this tutorial in section 2.1, without irreducible representations for the moment, because this will be introduced. So this is the input file, the input page for this program. Again, you introduce the space group, you introduce the K vector. There are options here saying I need more K vectors, so you can put several ones. You can, if you have a K vector, you can say, okay, I want also the symmetry related ones. For instance, if you have a tetragonal one, it can, the program directly tell you which ones could be also related by symmetry to the propagation vector that you have detected. By the way, if you are using powder diffraction, you will never be able to distinguish between structures where there are several K vectors which are symmetry related, and if you have several wave vectors which are symmetry related, the powder diffraction is not able to say, okay, it is a structure with a single wave vector, or all of the wave vectors that are symmetry related are involved. So in many cases, the refinement will be, you will get equal refinements, equally good with the two models. So you include then the K vectors. For instance, it says choose the whole star of the propagation vector. That means choose the whole set of wave vectors which are symmetry related. And these are optional things. You can forget about them for the moment. But you can, if necessary, include the bicomposition of the magnetic atoms, which reduce the possible symmetries, and so on. This is the output that you will obtain. For instance, for this example here, you have a parent space group P minus 3m1, and then propagation vector 1/3, 1/3, 1/2, and the magnetic atom is at 1b, okay? And these are apart, there are many, I don't remember exactly how many, but quite a lot of possibilities. Some of them are the maximal ones, and some of them are not. You can see it because the program can show you, as I show you, a graph with all the groups, and it shows you which are maximal and which are not. But let me show you very important information in this page. First of all, here is what we call the group-subgroup index. The group-subgroup index is the factor which relates the number of operations that you had in the great group with the number of the parent and the number of operations that you have in this particular symmetry group. And it is this is really a theorem. This is a really rule that you can confide. The number of types of domains that your structure is going to have is equal to this number, okay? This number of domains, of types of domains, may vary from 2 to whatever, okay? And in this case, for instance, is telling us that the number is 6, 12, 12, 24, 18, and so on. And it is divided in 2 types, 6 and 1. And for instance, the first one. The second one is 6 and 2. And these 2 factors is the change of operations for the lattice part and the change of operations for the point group part of the symmetry. That means that, for instance, here is telling me that I will only have domains that are related by lost translations. And these type of domains are the most boring ones, that they do not, you could see them in microscopy, in electron microscopy, but in diffraction you don't see them at all. Because the only difference is an origin shift of the structure. And this you don't distinguish in diffraction. But the important types of domains that are more important are the ones on the right, which is the change of point group. And in this case, you have 2, 2, and so on. That's the type of domains that you are going to have, and that we call sometimes, some people do not like it, but twinning. I mean, or rotational oriented or rotational related domains. So, of course, as the point group decreases here, the number of domains that you are going to have increases, of the number of types of domains. Of course, the number of domains in your sample depends on the experiment. Another type of thing which is important is this conjugacy class. Conjugacy class, it's very important to understand that the program only gives, this listing is one representative of a whole set of magnetic space groups, which are physically equivalent, and they will correspond to the different domains, in fact, that the system has, or the system can have. That means once you have a subgroup, you have different subgroups that are related with this one by what we call conjugation. And the conjugation is an operation which in fact relates the groups of domains, the structures which are domain related. So from the physical point of view, they are describing the same thing. So, and that's why from each conjugacy class, the program only lists a single group. But this is maybe not the group that, for instance, you are comparing with some report of some structure. Maybe the one that you have chosen is not the one that have chosen the authors to describe their structure. So maybe the symmetry group that you have to use is in this conjugacy class, but it's not the one that the program has chosen. So sometimes you have to go to this button, see the whole set, and see which one corresponds to the description that is of this structure. And the other column here, get irreps, I will skip it because it corresponds to irreducible representations, which we are going to talk in the following days. And it is something which is very important, but for the moment, summarizing what is going to, if you click there, the program is going to tell you which irreps are involved or are important for this symmetry break, for this arrangement and this magnetic ordering with this symmetry. And the next final column, you have to click if you want to make a model for any of these symmetries, then you click here and you decide that these are the models you are going to try in the same way that we done for the other program. The program, as I told you, can just show you all these listings of symmetries, and the one that is realized in this particular structure is this one here. So let's do it now. Ready? Do you have the zip file of this compound? Okay, good. Then we go to voila, here. We are here. And now we have to put the group, which you have to tell me, it's P minus 3M1. P this one, 164. I have chosen it. You have a button here just to choose. You don't have to know the number of the space group by heart. I mean, you can just go to the list, okay? And here I have to put 1/3. And 1/2. I can look here if there are more. I just recommend that always try here to this button here to see if there are other vectors related with this one. There are not, okay? So it is a single vector with no symmetry related ones that could make a multi-K structure. It says it in those cases that the pair of Km minus K, of course, they can be present, but I think, yes, I can put here Vico position. It was 2B, I think. No, what was 1B. Submit. So I've chosen the Vico position of the magnetic atom to reduce the possibilities, because then all the symmetries that force 0 for the moment are not listed, and then I submit. So here it is, the list. And here there is very important, here is list of subgroups which allow a non-zero magnetic moment in all sites, okay? If you are not so choosy and you also want solutions where maybe some sites are forced to be 0, there are 13 groups. If I go here to more options, I have non-zero magnetic moment allow at some Vico positions, not all coming from this site. So if I go here, in many cases you may have more possibilities, okay? So, and in this case you go into 17. This from 13 to 17 means there are some symmetries which will force at some of the sites that the moment is 0. People that know much more than me about magnetism, they don't like normally these solutions. Also, there are reports in many cases of structures where you have this type of structures. They justify them somehow by some frustration or some kind of things, but they exist. At least they are minority, but they are. So let's go back to the 13, which is less, but anyway. So I go back to here, which is the 13. And I think this is the graph that I've shown you. If I go, you press this button of the graph, then you get this 13. I don't know if this was the one or the 17, I don't know. But the point is that here is going to be our case. And again, here what I would do, I'm not an experimentalist, but what I would try, if I don't know the structure, I would try first these 3 first symmetries. And then if they don't work, I will go down to lower ones. But of course, the obvious thing is to try the ones with higher symmetry. And as I said, the one that works is this one here, okay? Which is the number 2, okay? This is the number 2, which, by the way, is polar. So this is, in principle, this is a multiferroic structure. So I go to this one, which is the number 2 here, and include the structured data of the parent phase. This is click by default. I submit to Mac Modelize. And now the program Mac Modelize is asking me for a zip file, okay, of the parent structure. So I go to my list, and I think it's this one here, no? It's barium, 3, niobium, and so on. So I upload this file, and now I have to indicate which is the atom which is magnetic, which in this case is a single one here, nickel. I submit it. And now the program knows which is the site which is magnetic, and now it's going to do the calculations, the symmetry restrictions on this, for this symmetry, for this group. Voila. By the way, let me go back to the, here, I didn't show you the conjugacy class. Let's see the conjugacy class for this PC3. You will see here, there are 6 different groups that can describe exactly the same structure. It's only, they are equivalent by lost operations of the parent phase. When people determine structures, the control of what is exactly the same structure and what is not, because normally you can refine and you obtain different models, and sometimes if the structure is complicated, you don't know at first sight if this is the same or not. The same in the sense that it is equivalent. Of course, you see that it is different, but in many cases it can be exactly the same one corresponding to one of these groups here, which corresponds to the same conjugacy class. Not very long ago, I saw in PhysRep-B some guys who just report, I refine and I got these 2 models, and with the nice pictures of these 2, and if you go, these 2 models is the same model, okay? So this is happening still today. And this is because if you don't use symmetry, you cannot control very nicely this possibility of having, there are many other cases where you cannot refine between 2 very different models and so on, but in this case, it is exactly, they can be related by an operation, a lost operation. Therefore, they correspond to 2 domains. So, but we were, where were we? Where were we? Where? Here. No. Here. So this is the output similar to the program MaxMan, where you have this, and now the only thing, you can click here to go to MagNest, which is a program to go into systematic absences, or to M-tensor, and so on. Here it lists the positions of the group, but for us, the important thing is here to go to the magnetic structure and to see how it looks. Here again, you have 2 degrees of freedom. One is on the plane XY, with a single parameter, with a special direction on the plane, and then M-set. Again, if you have the possibility of making the system planar instead of non-coplanar, you can try. And in fact, this is what happens. Or you can just look for M-set and look at M-set if it works. MZ is not going to work. What it works is the spins on the plane and the basal plane. And again, here you produce an MC file. And before working with this MC file, I recommend just to have a look how it looks. So what's happening here? Get an error, I don't know why. This normally does not happen. We've seen this type of well, let me see if I... Here you have the zip file that you can download. I will try in another way, but I don't know what is this. It's completely new. Well, the one that worked before does not work now, so it's something... It works? Okay. Okay, something that... So, if your computer has worked, then you must see something like this. Something like this thing here. Okay? Okay, so that's and your zip file will generate a zip file with this symmetry indicated by these symmetry operations, and also the zip file will contain that it is using a file which is 3A, 3B, 2C. Remember, the K vector was 1/3, 1/3, 1/2, so you have to multiply the unit cell to describe your periodicity of your spins, and this is 3, 3, 2, and then the transformation to standard is indicated also by the zip file in this way here. If you have done the zip file, you have it there, you can see it contains this. With this visualization, you can just change from the description in this 3 by 3 by 2 cell to the standard cell, and you will see it like this. The advantage of seeing the units, the structure in the standard cell, is that you get rid of these problems of distinguishing and confusing arrangements which are equivalent, because they all go to the standard, and the standard is the same for all, okay? If you do for all the other maximal subgroups, you will obtain this type of arrangement that they are indicated in the tutorial and so on. So let me just 5 minutes. Do I have still 5 minutes? Yeah. There are other programs that I mentioned, the MagNest for extinction rules in diffraction, which again, I recommend that you, if you are interested on this program and its applications, then just read this paper from 2012, where it is explained in detail. It can be used also for incommensurate structures, if you know the superspace group. And I want to stress this program because I show you here, for this case, which is in fact the point of the one that we have used for this example, okay? And you see for this example, if you go to the MagNest, you get this systematic absence. And you, of course, you have also this systematic absence, 00L, L any. This comes from the K vector, from the propagation vector. That means that as you have a propagation vector which does not mix nuclear and magnetic reflections, you will have the peaks, reflection peaks, completely separated from the nuclear ones. But we will have this systematic absence for this magnetic space group, which is the one that is realized in this compound that we have just shown. And please notice, this systematic extinction does not necessarily mean that atomic moments are along C. Okay? This is a thumb of a rule that many people use, just saying, okay, if I see that 00L is absent, then the spins are along C because of this rule of the diffraction that you have heard this morning. But this is not true, because what it should be parallel, it is the structure factor formula, or what you have called, what is the magnetic structure. Exactly. The magnetic structure factor is a vector, and this is the vector that should be parallel. And if you have this absence, it is because it's parallel to the Z axis. But it can happen, and in fact, for any magnetic space group, if your magnetic atom is in a general position, it is completely arbitrary, the direction. The symmetry comes not from the symmetry of this spin. It comes from the relation of this spin with the other spins of the orbit of the other atoms. And this makes the symmetry that forces this systematic absence. And this is this symmetry relation between different atoms will make that the magnetic structure factor will be along C or will be zero, maybe. Okay? And in fact, in this case, we have seen that the spins are on the planar base and on the XY plane. But still you have this systematic absence. Okay? You still have this systematic absence. It has nothing to do with this thumb rule works if you are thinking of collinear structures. If the structures are collinear, of course, yes, because then this magnetic structure factor will have the direction of the spins of this collinearity, but not in general. So this is what I show you here. Our atoms in this structure just are on the plane, and you have the systematic absence here. Well, and here are another example for a multi-K, but I think I can stop here because I don't have any more time. Thank you very much.
Thank you very much.